let's go ahead and get started. Okay, that one's not working. Okay, let's review algebra. But before we do, let's just say, Father, I'm frustrated anyway, but we have so much material to present. I mean, I could probably go on for 2 or 3 nights on this. But anyway, Lord, just be with us. Help me to teach and help everyone to learn. In Jesus' name, amen. Very good, John. Anyway, let's review algebra. How many remember this?
Yes.
Yeah. Let's just do this again. I'm just going to go over it. How many accept that A equals A, right?
Yes.
N equals N. Scissors equals scissors. 3 alpha equals 3 alpha. So if you add 3 scissors to 3 alpha on both sides, they stay the same. Then if you divide all that by N on each side, it stays the same. Now I added something to this. This is an equation. One side equals the other. Now I added this. Oops. If you divide alpha by alpha, that equals 1. If you divide N by N, that equals 1. If you take scissors and subtract scissors, that equals 0. And then again, just for confirmation, if you take 1 over N and you multiply that by N, you end up with 1 because the N's cancel. I mean, these are the real basic parts of algebra. If you don't get it, okay. We will do, but here's Joe's mathematics. Note, something divided by itself equals 1. 1 or anything over something times that same something is equal to 1 or the same something. Now, everybody follow that? And did. And I'm glad to have somebody who really understands. Now let's undo it. If we have 3A plus scissors over N, if we multiply that by N, that'll cancel the N. So we end up with 3 alpha plus scissors. We can see that. So then we subtract scissors from both sides, we end up with 3 alpha. Is everybody following me so far? Okay, so how do we get rid of the 3 alpha? To get it down to alpha.
Divide by 3 on both sides.
Divide by 3, right. That's basically all there is to it. If you get it, fine. If you don't, you've got some memorization to do. Memorize the little circle with the, let's say, a V on top and I and R on the bottom. And use that to figure out what the program ought to be. Okay, now we're going to review Ohm's law and power. Ohm's law, I hope by now you recognize this. Now, I was going to print out my notes, I didn't. Volts, or electromotive force. Volts is the what you call electromotive force, right? So volts, or the electromotive force, is the force. It's trying to shove current through a circuit. An amp is the amount of current that's flowing through the circuit. That's I. And then there's the tough guy, R, resistance. He tries to stop current from flowing. So there's V or E over I equals R. Or if you use algebra, whatever other combination. That's the only one I can remember. Some people can just name them off and they know them. And were you going to say something or just, okay, thank you. All right, now let's just move on to Ohm's law and power review. Now, this is something you must memorize. If you do not know what these are already, you need to memorize them. Micro, I finally found the micro symbol on my computer. Okay, there is micro. It's 1/1,000,000th of whatever it is. And as you see there on the right, if you're using a typewriter and you can't, or your computer and you can't find the symbol micro, which is Greek, use the letter U. Okay, and then there's milli. Milli is 1/1000th. We're just making sure we're recording.
Yes.
Everybody can hear me out there, good. And then there's normal, volts, amps, and current. And then there's kilo, which is K. That's the abbreviation, and that's 1,000. But if you hear somebody say kilo ohms or 100K, that means 100,000. And then there's mega or mega. What was there a question? No, okay. If you say meg ohms, that means 1,000,000 ohms or megavolts. That's a lot of volts. So know this. This you should have down. You should be able to repeat it at any time. Most of us who have been at this for years, it's just part of our vocabulary. But a major part of this whole class is learning the vocabulary. Okay, next. How to measure watts. Now, watts power, which is power, and the measurement for power is watts. It's either the current times electromotive force, or in what it's measured in volts. Current times volts is equal to the power. And then there's power equals RI squared. And we know when we square something, we're just multiplying I times itself. I started to say twice, but that wouldn't be quite right. Just I times itself. But you know something? I don't know that I've ever used that formula. I just have not. But this last one, power equals E squared, or the V squared over R. That one you need to know, because that tells you what your transmitter's putting out. Has everybody got that? Okay. Now, if you do not remember how to do it algebraically, here's the great circle of power. We've got in here E or V, volts, current, resistance, and power, and all the associated ones. So if you have if you know two things, usually you can figure out the rest. This is something you can go online and just say Ohm's law, symbols, or something of that sort, or just Ohm's law, and you will find 24 of these. But be warned, we know at least one of them out there that is wrong. Thanks to John. Oh, I would have never seen that. Okay, decibels. Now, dB, decibels, is an extremely important concept. We need to understand what it means. Some of us will learn how to work in dB and be able to figure things out. Some of us may never get there. But if you understand what people are talking about when they talk about dBs, that's what we want you to learn. So there's two kinds that are major. There's power, which is if you got 5 watts and you go to 100 watts, that's a 20 dB gain. Now, and if you, the other kind is in volts. Now, power is current times voltage, right? That's something that's multiplied. It is volts times amps, and that gives you power. So in that, it's 10 log power 2 over power 1. If you've got a scientific calculator on your phone, which most of us do, you can figure it out the hard way. This is the hard way to do it, but some people have no trouble with this sort of thing. But dBV, which is volts, and dBU, which is used for audio work, that's volts. And that's 20 log, the one value over the other. And let's look at more practical applications of these. One of the spaces you're going to run into this is in antenna specs. And it'll have to do with the gain of an antenna. If you've got a dipole, you can consider that a gain of 1. Or if there's an, I believe it's called isotropic. Is that correct, Daron?
Yes, it is. Sorry.
Oh, no problem. Yeah, probably had to unmute.
Yep.
If it's an isometric antenna, which is an imaginary antenna, imagine a coax going up and being connected to a little pinhead. And that's the center of your antenna. Now, antenna manufacturers use that. They should not, because a dipole was the only practical thing out there to start from. But you get what I think it's about 2.3 dB for a dipole over an isometric pretend antenna. But the specs that you get when you go to purchase an antenna or you're searching for one, it's in dBi. And dBi is a reference. So it's referred to the gain over an imaginary antenna. So we have to, yeah, I know, it's crazy. But somebody did it, right? And so everybody else had to copy it so they could keep up with it. Because the difference between dBi and dB, what I think it's dBd for dipole.
Yes.
I think it's 2.3 dB.
Somewhere around there.
Yeah, thank you, Daron. So, I get frustrated with this, but that's the way it is in the industry. That's the way economics work. Often people have to make it look like it's got the most gain. But in reality, when we're looking at an antenna, we want to know really what the gain is over a dipole, because that's our normal minimal application. Question.
Yeah, so that was, again, that was DPD, did you say? DD over dipole?
Small dog over big Bravo. D as in dog, dipole. Here in a minute, I'm going to show you a chart that shows all the references. This is something you don't need to memorize, but as you're working with dB, you will start learning it. And
so I just want to make sure I understand. So when you say gain, it's the gain in power that the dB is measuring. Is that correct?
that is correct. Yeah, say you've got an antenna and you're pumping 50 watts into it from your VHF transceiver. And if it's just a standard vertical with a ground plane, that would be the gain of a dipole. If you got a Yagi and it had a 6 dB gain over that dipole, that would be 3 dB, which would be double. So you go from 50 to 100 watts, which then again, 3 more dB would make it 200 watts.
So how do you know what the gain is against? So you have this antenna and you're measuring gain against something else. So how do you know what the something else is?
Against the dipole.
It's all against the dipole?
Yes, like it's a standard.
Okay.
Well, except that the specs that they give you, actually, can you see my arrow here? Let's go down here. See this gain dB?
Yeah.
Oh, that's, that is probably dBi. Which means the gain over an isometric antenna. which is-
Isotropic.
thank you, isotropic antenna. Which, as I said, is a pretend antenna.
That's theoretical.
Theoretically. I'm going to call it pretend because, hey, well, engineers use it. I don't think it's of much use, but you need to be aware of that. You need to ask the question when you see the gain of something. Okay, a gain of amplifiers, and this is the one that I really like. Anybody who ever has heard of EME or Earth, Moon, Earth. I mean, we literally take big antennas, aim it at the moon, shoot a signal out there. About 2.5 seconds later, the signal comes back to the Earth, and it's lost 250 dB. I mean, that path loss is major. And you have to overcome that either by the transmitting antenna and the power you put out and or how you receive. And if you got a lot of noise in there, I mean, these are things that are getting very sophisticated. You can't copy it. But can anybody tell me who made JT65? Dr. I can't think of his name, but JT65 is a program that permits you to pull signals out of the noise. So they use JT65, smaller antennas and smaller power.
Joe Taylor.
Joe Taylor, that's it. JT65. It would take a full second to send a signal. And then it would go up to the moon and bounce back, and it'd take a full second for the computer to decode it. Excuse me, that's not correct. The receive signal is full second long, but it would take the computer a while to decode it, and then it could read the signal. But the JT65 and JT8, which is a very popular method now for HF communications, can pull the signal completely out of the noise. You can be sitting there listening and it sounds like nothing but noise. And this program will pull the signal out of the noise. We just recently went through a low sunspot cycle. We've talked about that a little bit. And communications were terrible. People started using JT8, or maybe that's not it. But they started using that, and they started talking to people all over the world because the signal was there. It just wasn't strong enough for voice communications. Anyway, audio, microphones, speakers, all kinds of stuff. It's usually measured in the same thing as voltage. And a VU meter, you've all seen them on tape recorders and that kind of stuff. That's a different thing. And when you look at your radio, there's an S meter that reads S9. S9 is 50 microvolts, or supposed to be. And if it does that, if it drops down to S8, that's 25 microvolts. Is that correct? Oh, it's 6 dB. Yeah, I think that's 6 dB. Anyway, moving on. Darren, I'm hoping I'm not getting into your talk. Darren is going to talk.
Nope, you're fine, Joe.
Oh, good, good. Darren is going to give us some examples of dB and how it's used. But dB has a slick thing. There's, of course, the power ratio, which we've talked about, and then there's the voltage and volume ratio. If you double the power, that's 3 dB. If you double it twice, in other words, if you go from 5 watts to 10 watts, that's 3 dB. If you go from 5 watts to 20 watts, that's 6 dB. If you go from 5 watts to 40 watts, that's 9 dB. If you go from 5 watts to 50 watts, that's 10 dB. Once you start getting these into your head, you start understanding what people are talking about. And the thing is going from 5 watts to 50 watts is exactly 10 dB. When you double it, it is almost exactly 3 dB, but it's not. But don't worry about that because it's like a fraction of a percent difference. So anyway, now if you go, if you go, yes, if you go from 50 watts to 500 watts, that's 20 dB gain. And then over on the audio side, if you double or half the ratio on the right-hand side of the screen here, ratio of voltage or volume. If you have an S9 signal, which is 50 microvolts, if you half of that, that's 6 dB, and that's S8. If you do that twice, that becomes S7, which is 12 dB, and so on. And we'll be demonstrating that here momentarily. But I want you to see this chart. I don't want you to memorize it, but these are absolute dB units. And dBm is the most common one used. And that's dB compared to 1 milliwatt. My signal generator, which I'm using to feed this receiver over here, which you're going to see in a minute, is in milliwatts. So there's dB large W watts, and it just goes right on through the various kinds that you can like that. About halfway down is dBV, which is volts, which is also on the signal generators, if you ever do that. So if we go to the next one, these are relative units. And you're right. Is it just a ratio? If you're talking about watts, like I was talking about 5 watts, 10 watts, 20 watts, 40 watts, that's just plain dB. Everybody thoroughly confused? Bruce is back there shaking his head. Yes, good for you.
Let me honest with you, laddie.
Yeah, well, sometimes it is, but when you start working with it, it starts making a lot more sense. So, and let's see, what have I got next? Okay, not yet, not quite yet, Darren. You're next, though.
What?
Okay, here we see S9. And I'm just slightly over, I see. Now that's 50 microvolts. Follow that? And this is what you're going to have on your radio. somebody's transmitting to you, and if they're hitting you at S9, that's a strong signal. And that's above most noise, although sometimes in the city on 80 meters, you get an S9 noise level, which is just, I mean, it's just almost impossible to deal with. But if we decrease the level down to S8, now that's a 6 dB in voltage drop, which is half of the voltage. So now we're looking at 25 microvolts.
But what did you decrease?
The output of my signal generator.
Oh, okay, okay.
Oh, that's I had to repair my signal generator, and I've got it working now. Last week I had a funky old signal generator that had been donated to us, and I had to do all kinds of things to get it put out as low as S9.
Okay, in the real world, Joe, you don't have a signal generator. We're receiving a signal from another station. So you're saying that at S9, we're receiving 50 millivolts from somebody?
Microvolts.
I mean, microvolts?
50 microvolts, correct.
Okay.
Okay. Now an S8, or if I continue to drop it, let's go down, and I'm lowering the output of my signal generator. We'll go down to S7. That's still a strong signal. Scott, do you like getting S7 signals?
Oh, you bet.
Yeah, yeah,
I like anything above an S3.
yeah. Well, let's see how low I can go here. Oh, I'm gonna have to. Okay, there's about an S3. I lowered the output of the signal generator a lot. Now, if you have no noise and you're getting an S3, if somebody's asking for a signal report, you're an S3, but you're a Q5. Q means quality. So you tell them you're an S5 you're an S3 Q5.
So I'm
Are-
sorry, I got lost.
Okay,
What is the scale of this 1 to 9, 20, 20, 20, and 40? What?
that's volts.
Oh, volts, okay.
So it's microvolts. S9 is 50 microvolts.
So why are we using 9753? Why not just put those numbers on?
Because a lot of the displays are not calibrated. A lot of the radios aren't calibrated. For one thing, and it's a standard thing to give a signal strength report. So it's an arbitrary scale, honestly,
To
that is
convert the-
calibrated. This calibrated on a lot of radios so that you know if it's S9, it's X amount of volts.
So it's a convention.
I would say so.
Uh,
Joe may disagree.
No, and I agree with you. Although most of the rigs today are pretty accurate in that you put in 50 microvolts and it comes up S9.
Okay.
But the thing is, if it's reading S5, it's probably not the same from one radio to another, because most of them are not linear, not linear is not the right word. But they're not, the radios are not consistent as they should be, but if you've got a decent radio, it's going to give you a fairly good idea of what it is. So, and if you go to +10, that means it's 10 dB over S9, which means it's a gain of you go from 50 microvolts to 500 microvolts at +10. Now that's a pretty strong signal. Remember what's happening is you got somebody across the United States and they're sending out a radio signal, and it's going all the way across the United States, hitting your antenna and creating 50 microvolts. because the signal gets induced into the antenna, which creates a voltage that your radio is able to receive. But we're going to get into all that detail much later. Does everybody understand how their S meter works? And Scott, will you tell me how you properly respond to somebody with a, say, an S? Just describe how that happens.
Sure. If it was just a mild signal that I was getting in from someone, I would say this is W7 PMF and JA6 TUV. This is W7 PMF, and you ask for your signal report, and it's a 5 and 5. And I thank you very much for the signal report that you gave me of a 5 and 8.
Okay,
That's
well,
what I
what's the
do.
5 and 8? What does that mean?
That 5 and 8 means I've got a pretty nice signal. Yeah,
So it's
okay,
easy to copy.
and it's easy to copy. Oh, first of all, the 5 means that it's very nice audio, very, very clear. And then the signal strength, I can get off my S meter and on my radio, and I gave them a 5 and 5. So that's a decent signal report.
If you told them it was a 5 by 9, that would be a very strong signal.
That's right. And I never have to tell a person that it's X number of microvolts on the radio. All right. All I need to do is, all you're looking for is a comparative signal report. You know, when I'm talking to somebody in Japan on this particular day, how am I coming? Average, good, excellent, you know.
So the first number is what you perceive
The first,
orally, and the second number is what you get off this
Yes.
signal
It's the
thing.
quality of the signal.
Okay.
Yeah,
That is, unless you're doing contesting, and then 5 and 9 doesn't mean did.
yeah. If you're in a contest, what is accepted is you give everybody a 5 by 9 signal, no matter how bad it was. You just, I mean, that's just done, you know, and
Courtesy.
well, it's not a courtesy, it's just because it's fast. Some of these guys run 60 or 100 contacts in a minute, right? I mean, it just they just go through them. This is NJ7OK. You're a 5 by 9, 7 3s. That N7RQQ. This is NJ7OK. You're a 3 by 2. No, you're a 5 by 9. And everyone's a 5 by 9, 5 by 9, 5 by 9. And that's how fast, I mean, they just whip through them like that. And that's not exactly what happens, but that's close. So, but let's see, I was going to say something else, but I think that's it. Darren, are you about ready, my friend?
Now you will.
It depends on what you want me to do, Joe.
I talked to Henry Sherman of Vendome.
All right, can you hear the audio?
Regarding the cost of converting the Bell of Anderson distillery
That's a little bit low.
alcohol, wrote Creel Brown Jr., president of JPS.
I think
Brown, to Taylor
I think the
Hedges.
Zoom is going to regulate it anyway, but
Their firm has just recently completed.
what I want to show you is on the radio, as we decrease signal strength, what the noise is versus the signal. And we'll talk a little bit about the dB, how many dB is involved. So first thing I'm going to do is reduce our signal strength. You can see the S meter dropping down there
Yep.
till the signal is so low that the squelch is kicked in and silenced the noise, okay?
Yes.
So now I'm going to increase signal strength. So that starts to hear at about negative 120 dBm. So that'll kind of be our reference point where we opened the squelch on this radio.
Now, are you using a signal generator to do that?
Yes.
Okay.
So that is 119, negative 119 dBm there. And then I'll turn it up to, we start watching the meter, the S meter go up here. And I looked at this earlier and it jumps from S1 to S3. It takes about 4 dB of signal to do that on this radio. So we'll see what that sounds like.
The war production board slowly changed diverted sugar and grain for industrial production
Okay, so there's S1.
plants instead of outfitting Burbank stills with special rectifying columns.
Is there a fair amount of noise, Joe, that you can hear, or is the Zoom part cleaning that up?
It must be cleaning up because I don't hear any noise.
It also made industrial alcohol for the Canadian munitions and supply department. So effectively, most North American distilleries were producing war alcohol. The war production
There's
board
S3,
indicated that it wanted 90%,
S5,
leaving hope that whiskey production could
7,
continue in the time of war.
and all I'm doing is turning up the power on the signal generator, so it's a stronger signal.
The government needed all in
I was afraid that Zoom might clean that audio up, so we can't really tell the difference of the noise.
No,
war materials. It's a matter of critical necessity, wrote Congressman Robert L. Dawson, the chairman of.
So what I found on this radio, Joe, and going from S1 to S9 was 15 dB. Was the difference to get from S1 to S9 on this old Kenwood radio. That's why I was saying not all of it is as calibrated as we.
yeah,
Like-
you know, Darren, I'm sorry, but you know, I think the difference is I work on HF radios.
Yes,
You work on VHF radios. And I think it's the HF radios are more sensitive to getting stuff right. In
I
that particular
suspect you're
area.
correct.
Yeah,
Okay, so let's look at a little bit of the practical application of what I find handy for decibels. And then we'll do it a little more practical for VHF. This is just a diagram when we first started using microwave, essentially 2.4 gigahertz to get from Tillamook to Mount Hebo to get signals up there to do things. And when you determine what you need for antenna gain and power, you usually just build a diagram like this that shows all the components and what the loss is. And we'll start over here. Hang on if I get my pencil working here. We're starting over here with a transmitter and a 1 watt amplifier, which would give us a plus 30 dBm out for our power level. There's a nice little graph you can look at on the internet that compares watts to dBm, shows you how to convert that if you want.
yeah,
But if we-
dBm is 1 milliwatt. So 30 dB is 1 watt, correct?
Right. So we start out with 1 watt there. We've got some feed line that we lose 2 dB. So now we're down to 28 dB for our signal strength.
Yeah,
Does that make sense?
yes.
We just subtract 2 dB from that. We've got an antenna here that has an advertised gain of 24 dB. So that takes us from 28 back up to 52. So now our signal leaving the antenna is 52 dB. The path loss in, I think it's
You
18
can't
miles.
quite see the top of your paper.
Oh, sorry.
There you go.
18 miles, I think, is the path. And that loss, yeah, right there, 18 miles, 130 dB. That's a lot of signal we lose going out in free space for 18 miles.
Now, do you calculate that or do you measure it?
That's calculated. There's lots of online calculators for that.
Okay.
And it's frequency dependent. So we lose more signal at higher frequencies than we do at lower frequencies.
Yeah, Darren, you're working, you need to explain you're working at microwave frequencies, and what frequency are you at?
Yeah, this is 2.4 gigahertz. So these calculations, the feed line loss is dependent on the frequency, as is the path loss. So by the time we get up to the top of Mount Hebo, our signal strength is negative 78 dBm roughly. And then we have the same antenna, so we gain 24 dB. So now we're down to negative 54. We have another piece of feed line where we lose a couple more, so now we're down to negative 56. A lightning arrestor that loses 1 dB when you put it in the circuit, so we're down to 57. And then because there's other equipment up there on the hill, we have a bandpass filter, so we only hear our radio. But that costs us 3 dB, it looks like. So now we're down to negative 60. We get a little boost from a preamplifier that's in the amplifier at this end, so we're back up to negative 54 dB. So that's our signal going into the radio up there on the hill. And because this is data instead of voice, there will be published rates that if you have a signal of negative 65 dB, for example, that will equal 10 megabits of data, for example. And it's just part of the data radio that says, I needed this quality of signal in order to give you this much bandwidth. And maybe it's at negative 85, you get 5 megabits. Negative 95, you get 1 megabit or something. So in order for us to figure out how much power, antenna gain, and everything we needed, we do that all just by adding subtracting the dB loss and gain in the system to make sure that when it gets up there, we have enough signal to get the full bandwidth.
So if you wanted more data bandwidth, you would apply power somewhere.
Correct. So that could be done with higher gain antennas,
Uh-huh.
lower loss feed line. I can't really shorten that path. Or I'd have to increase transmit power to get the signal up. Does that make sense?
Yes.
Okay. I'm surprised. That's good. That's very good. It made some sense. Okay, so let's look a little bit at the basic, if we were to put it into something that we might use. I'll do my very technical illustrations here, almost left-handed. Here's our 4-watt little radio that we're going to use. So we know that that is 36 dB that we're starting with. We're going to run it through a little bit.
dBm, right?
Sure.
Yeah.
Sure.
Joe's trying to catch me.
Yeah.
So we're going to run it
So
through some,
just so they don't lose track.
right.
This is an actual reference to 1 milliwatt.
Yes, this is the measurement of power for 4 watts coming out of the radio. So then we're going to use a lengthy piece of feed line that's going to say lose 3 dB in that feed line. So now we have 33 dB when we get up here, right? And we're going to use a nice J-pole or something which has essentially no gain to it whatsoever. So our signal leaving here is going to be at 33 dB. Our path loss, we're going to go up to the repeater,
We're
which is
losing
100.
on the top.
Sorry. 120 miles. Oh, no, 120, 100 and let's not do that. Joe messed me up. Let's start over. 20 miles up to the repeater. And the path loss for that is 105 dB. So now up here at the, probably off the page, up here at the repeater, by the time it gets there, it's going to be minus 72, where it gets to the repeater antenna. But that's a pretty good antenna. That's a 6 dB gain. Oops. Antenna. So now we have negative 66, right?
Yes.
Yes. And we have a longer run of feed line. So we're going to lose 3 dB in that run of feed line again. That gets us down to negative 69. And then we're going to have a duplexer up there, which is tuned cavities that allow us to transmit and receive at the same time. And those are lossy. That costs us some signal. So we lose 3 dB in the duplexer. So we go from 69 down to negative 72 at our receiver, which is a very respectable signal. The receiver will hear all the way down to negative 110 or so. So if you're trying to figure out how much power and antenna gain you need for a system to get connected, this is an easy way to do it. It's not foolproof because this loss figure here is free space. So I referenced those FRS radios that you buy at Bimart that say they'll go 45 miles. They will do it if you're on Mount Shasta and the next mountain 45 miles away and there is nothing in between you. Yes, they will go that far. But most of our terrain here interferes with this free space loss. So we lose a lot more than 105 through all the trees and everything else we're going through.
So are these loss points at the receiver, at the repeater side, are those published? Where do you get those?
I just got them out of my head.
No, but I
But-
was gonna say, if I wanted to do this calculation for my antenna, I would need to know
Sure.
data on the right-hand side for the repeater. So
Yeah.
can you actually get that data?
I could provide you with that data for most of these. I don't think it's anything published because it varies quite a bit from repeater to repeater.
Uh-huh.
But and
So-
the type of receiver will have different sensitivity. There's also other components that are in here. There's a lightning arrestor in here that drops it a little bit that I didn't really put in, but yeah.
How do you know, how, so that the 3 dB loss that's assigned to the feeder line,
Yes.
how do you know that number?
Okay, so that's dependent on the type of coax, and Joe had a chart up there earlier.
Correct.
So yeah, there's a published chart for various types of coax per 100 feet at a particular frequency.
Oh, okay, I see.
So we would just look up if this is a very common one is what's called LDF, if I could write 4, which is about 5/8 of an inch on the outside diameter, pretty good sized stuff. This is about 5/8. And so it's published what the loss is for every 100 feet of that at 150 megahertz, which is pretty close to what we use.
Okay,
So we would do that calculation. And there are more depending on how detailed you want to get. Every connector actually takes a little bit of loss as well. But just for rough calculations, this is a way to do it, and where the
At
DB
100
part comes in real easy.
At 150 megahertz, those losses are negligible.
You would think so, and I would agree with you, but the
But
state of
it's
Oregon,
curious to me that you start out with a positive number and you end up with a negative number, so that's a pretty,
that's
a
that
pretty,
free space loss.
yeah.
Yeah, that eats up a lot.
I guess where I'm astounded because I didn't realize that receivers could function at that far of a deficit.
Yeah. I mean,
Yes. So this, when we were playing with this one,
As pre-war bourbon.
let me turn it down here and see where it goes away.
2,500 bottles in a whiskey galore pre-war bourbon sale. Full quarts of Walker's Deluxe Illinois Straight Bourbon whiskey.
That's negative 121 dB right there,
so-
where it goes away.
But like local
So not very much power it takes to open that receiver up a little bit and get a signal in.
Yeah, and that's well under 1 microvolt, correct?
Yeah, let me see. 0.25.
Yeah, 0.25 microvolt.
Yeah.
At the radio antenna input.
Right. So one thing that might, I mean, if you think about this, we didn't really talk about effective radiated power, did we, Joe?
No, we have not. And that's
Okay.
something we'll cover in detail, but go ahead and briefly give us
Yeah, you'll hear ERP a lot, or effective radiated power. And you can think about this with the FM broadcast stations where they advertise they're a 100,000 watt station. They're quite likely not a 100,000 watt transmitter. They're quite likely using a smaller transmitter to an antenna that has quite a bit of gain. And that gain adds up to an effective radiated power. So if you started with, I should probably stay with the repeater example, but I won't be able to do the numbers quick enough, Joe.
But just start out with 1,000 watts.
Okay, 1,000 watts. What if we have a 9 dB gain antenna?
Why don't you make it 10?
Let's make it a 10 dB gain antenna.
That's easier to do.
And assuming this is a real short feed line, how many watts do we have now?
10,000 watts.
10,000 watts of effective radiated power. Okay, because we've taken the 1,000 watts and we multiplied it with the antenna gain. So you'll hear ERP a lot, and especially with fixed stations like repeaters and microwave systems, because it's not really 10,000 watts at the transmitter. We're just making that gain in the antenna. We haven't really done anything with antenna design or gain yet, but we'll show some point we'll get to that, right, Joe?
That is correct, yes.
So does that mean you can build an antenna of whatever gain you want it to be within reason?
Within practical, yeah. So I'll do my horrible illustration here. I'm sorry, but so this is our dipole. And if you can imagine, we're looking at this as if you're holding the dipole out in front of you. The antenna pattern looks like a giant donut, except it's a little more even than that. So it's like a giant donut all the way around the antenna, if it's a low gain antenna. To get that gain, we electrically squish the pattern out to where it goes like this. If that makes sense. It's kind of like taking a flashlight and taking the reflector off of it, and just holding the flashlight bulb up in the room. And then if we put that reflector on, we can focus the flashlight energy anywhere we want and gain in that direction, but we lose it in the other directions. So with this, chances are at 45 degrees up in the sky, we don't need a lot of signal. There's probably nobody hanging out up here at 10,000 feet that wants to talk to us. So if we use a gain antenna, we get that signal squirted out horizontally down to the floor, the land where the people are. Does that make sense?
Yes, sir.
Okay, so the farther we squish it, the more gain we get in those directions.
And that would be a vertical antenna with gain.
Yes, correct.
Yeah.
My 3D drawing is not very good.
No, that's great. So
But that's the practical part of DB for me.
well, that's good. Folks, for you who are thinking about your technician license, don't let this break your brain. You will, as I don't know how to say this. It's not necessary for you to know this, but if you hear people talking about it, you'll have some idea of what they are talking about. So, Daron, we're going to be going to break. So after we come back from break, we'll talk about capacitors, and then we'll do a capacitor experiment like you're showing there. Okay?
Okay, sounds good.
All right, and now we got about 3 minutes, but let's go to break right now. And we'll come back in 10 minutes. Thank you. We're now going to start talking about capacitors. Next week, I will be better prepared, although I prepared. I really want to show you AC and DC on an oscilloscope. And I thought it would be easy to do with what we've got here. It just was not working. So I'm planning on doing that next week. Next week, also, I am going to show you how to check the power of a RF rig. And it's easy to do. We're all set up here to do it. So if anybody pays any attention, they can figure out how to check the power of their transmitter. So anyway, let's get started with capacitance. So capacitors. Everybody's got that, I hope. So move up. Okay, capacitors. We've talked about resistors, and they basically they do one thing, they just resist. And we use it in AC, DC, all circuits. If it's a really good resistor, we don't have to worry about any inductance or capacitance being added in, and they just divide and divide. But capacitors, these are magical devices. They do all kinds of things. They can be used to store electricity. And when they store electricity, they filter out stuff. If they're used in a power supply, they filter out the ripple that would be in the power supply. Any of you ever, many of us are old enough to remember old tube radios. Do you remember the ones that would go, hmm? Well, the filter capacitor was going bad in those and you needed to replace it. But that's one of the things capacitors are used for. They're used for all kinds of filters. We will get into those much later in there. They're used as a DC blocker. They block DC. DC will not go through a capacitor, but AC will. So they're an AC passer, and they can be used as a timer. So there's lots of uses for capacitors. Now, this is what I wanted to show you, and I cannot tonight. So, and I apologize, but let's move on. I was going to show you DC and AC, explain what RMS voltage is and what frequency it is. And we will do that next week. So, but to get us started, I will not do the demonstration, but I will show you here on the screen. Here is AC. Notice the line right horizontal through the middle. It's made marked 0. That's 0 volts. So first the signal goes up and it's going positive, and we'll just say it's going up to 1 volt. And then once it reaches 1 volt, it turns around and it starts going down until it passes 0 volts. Then it goes negative and it goes down until it gets down to -1 volt. And then it goes positive again, goes back up to 0. Now, if you take that and you multiply the voltage peak, notice, see the one right in the middle? There it says VPK. That's the voltage peak. On an oscilloscope, you can read that real easy. And then there's voltage RMS. Now, the voltage RMS is a DC voltage equivalent of what that AC waveform is. And so now I think my next slide, yeah, well, no, this is, let me explain this. There's voltage RMS, which is 0.707. There's voltage peak, which is from 0 volt to the top of the voltage side. And then there's peak to peak, which is from the positive voltage all the way down to the negative voltage. And we will be going over this again later. And we will be showing you on an oscilloscope how this works. And there's voltage average. I've never used voltage average. I don't even know why they are using it. Yes.
What does RMS stand for?
Oh, root mean square.
Thank you.
Did somebody ask that question or did you ask that question?
Well, I am somebody and I did ask the question.
Well, you don't count.
Oh.
You're the moderator.
Oh, no.
Oh.
Nobody-
Careful,
Platform.
you know, he's a volunteer.
Oh, John, I couldn't do this without you. Thank you. Next slide, this slide. Okay, let's talk about RMS voltage. First, let's look at the purple area. That's the area that's underneath the AC signal. See, it goes from 0 volts at the beginning there where it says 1 cycle. It goes up and it goes up to, well, this is 120 volts AC or 115 volts AC. It goes up to a peak of 170 volts. Then it goes back down to 0 volts. And then it continues down to minus 170 volts and then back up to 0 volts again. That's 1 full cycle of AC. Now notice the green area. There they're measuring DC. The green area is the exact equivalent of the purple area. So the amount of power that is generated in the purple area is the same as the amount of power generated in the green area. So if you're taking AC, which is purple, and you want to figure out what that would be if you did it in DC, it would be the green. That happens to be 115 volts RMS. If you take 170 and multiply it 0.707, it'll come out 115.
Why do you care about that? I'm asking.
And he is someone.
Right.
You guys are more fun. Thank you. Remember the formula that I said you have to remember and power equals? Does somebody tell me what that formula is?
Power equals E squared over R.
Right. The FCC has said that we can have up to 1,500 watts peak envelope power. And we figured that out by taking E squared over R, except that we don't use the peak, but we can see it. If we talk into the microphone on a radio and look on the screen of an oscilloscope, we can see the peaks. So we take that peak voltage, multiply it times 0.707. Then whatever voltage that we get with that, we square that and divide it by 50 if we're using a 50 ohm load by the resistance. So that's E squared over R. And that's how you get your peak envelope power. And that's how you figure out what your maximum 100 watts is, or your 1,500 watts is. Or if you're just trying to figure out what a radio puts out, it's rated, most of them are rated, and we call them barefoot radios, 100 watts, peak envelope power. So that this stuff is important to you because this is how we figure out what the power output of our radio is. I've got 2 radios sitting over here right now, which I will show you next week, and we will test their power. One of them's 100 watt, and the other one is 50 watts. And so I will be looking for a volunteer in this room to check one of them. Does everybody hear me? Oh, good. I won't ask John. He hid behind his computer. Anyway, that's the reason it's important.
So where does the 0.707 come from?
You know, I cannot tell you.
Okay,
I just
just one of
learned.
those numbers.
Well, no, actually, if I still remembered my calculus,
Yep.
I could tell you. But I don't. And so I can't tell you, but through calculus, you can figure out what an AC signal turned into DC would be. And the number is 0.707.
Okay.
Any other questions? Okay. Now, this is, it's kind of fun. Here's wavelength and frequency. Notice the high frequency, it happens a whole bunch of times across the screen. Medium frequency a few times. And then a low frequency, just one cycle. Notice the distance between the peaks. If you're looking at an oscilloscope, that shows you the time difference from one spot to the next. That also could represent wavelength. And when we start talking about our antennas or frequencies and what the wavelength is in antennas, that will become an important concept for us. And hopefully next week, I will actually give you an audio example of this, and we'll watch it on the oscilloscope. You'll get to hear it and see it and watch it. Now, here's the wavelength. High frequency, you'll get a short wavelength. And remember, we're talking about 2 meters, 6 meters, 40 meters. That's our wavelength. So a high frequency gives you a short wavelength, and a low frequency gives you a long wavelength. Now I'm going to throw this at you. Imagine a radio signal that is 9 cycles per second. 9 cycles per second. They are literally doing that, and they are sending a signal all the way around the world doing it. At low frequency, it just hugs the earth and goes right on around. I can't give you the demo. On to capacitors. A capacitor is essentially 2 plates separated by a dielectric. The dielectric can be air, vacuum, paper, and let's see if this, yeah, okay, this is good. Here, watch this. See all these capacitors here? These are all different kinds of capacitors with different kinds of application. This is an electrolytic capacitor. It has foil in it that's rolled up, and in between the foil is paper, and the paper is soaked with a chemical. And when these are formed, they get polarized in one direction. When they get polarized, their capacitance increases. So these are the kind of things that you find in power supplies. This one and this one here. This one's got screws on the top of it. You'll find them in big transmitters and that kind of thing. This one has a little terminals here on the top for mounting on a circuit board. You mount it on the circuit board, soldered on the bottom, and it's done. Here's an electrolytic capacitor with wire terminals. This is a surface mount, a little tiny thing. This is a motor start capacitor. We won't do that. This is, I call these safety capacitors. You will find them at the input on equipment. They keep noise from coming in on your AC line or getting out either direction. We're going to skip that. That's 2 capacitors in one. Here's a surface mount capacitor. Here's a surface mount capacitor, smaller one. Now, here's a ceramic capacitor. Here is a polyester capacitor. Here's a polypropylene capacitor. And here's a polystyrene capacitor. These are all different kinds of dielectrics. They all have different kind of characteristics, applications. I mean, it can go on and on and on. You could you can get a master's degree in explaining capacitors, and we're not going to do this. This is, and I told you guys about this before. This is a memory backup capacitor. This is probably 1 farad. Most of the rest of these are like this. This one might be 40 or 100 or 200 microfarad. This is 1 whole farad, and it's typically 5.5 volts. So you put it in a system, and if the power goes down, it will keep things alive for quite a while. Little trimmer capacitor. And okay. Now let's look at capacitors. Here's a box full. So I'm gonna start with this guy right here. Note, oops. Here, let's get this turned around. Notice the plates. Remember that I showed you a picture of a capacitor and it just had 2 plates. Well, this is one set of plates, and this is another set of plates. These are all hooked together, and these are all hooked together. These are insulated from these. This one here is on this bracket, and this one normally would be grounded. Through this one, it's screwed down, or you might put insulators on there and have it insulated. And then these are the rest. This is a variable capacitor. By going like this, there's very, very little coupling between the plates. So this would be a very, very tiny. This would probably be something in the neighborhood of maybe 5 picofarad or we used to call it microfarad. Now, what is micro?
A
A
million,
million. So if it's micro,
a million millions.
right? And they call that, now they call that picofarad. So as we increase this, as we turn this, the blades get more meshed. So we just keep going and we keep going until they're fully meshed, and that might be, I'll just say 30 picofarad. I'm just guessing. We have machines that just print out and show you what this actually is. So there's a capacitor. Speaking about variables, here's one. More plates. And actually they're closer together. We can see there's a lot of space between there. Here they're closer together, and as you rotate it, you change the capacitance. So here you can easily see how capacitors work. Just another one. These are real close together. You would not want to put a lot of voltage on that because it snap across. Here you could probably easily put 1500 volts on this and it would not arc across. So this is for high voltage. This is much lower voltage. Now, here are a couple of electrolytic capacitors. These are solder type. This one is 35 volts, 220 microfarad. And it doesn't say what its rating is. Usually they're somewhere around plus or minus 20% or more. But that's an electrolytic. And this is another one. See, that one's 35 volts, 220 microfarad. Here is, boy, here we go. 35 volts, 22 microfarad. And we can see the leads. Now notice this side here that's got a little. Come on, focus. Well, all right. That's a little negative in the middle of it. This stripe here means that's the minus side. Electrolytic capacitors are polarized. You have to be careful to put them in right. Darren and I discussed him blowing one of these up for us. But we decided that would not happen. One of the reasons is when I was in the Navy, and stop me if I've told you this story. I was out in the front area and there was a steel security door between me and there. And I heard a large explosion. I went back into the operation room and most everybody could hardly hear anything because of the explosion. But what had happened was an electrolytic capacitor exploded inside of a piece of equipment. And when it exploded, it was a rack mount. If you know a 19-inch rack, it's a panel that's 19 inches wide. And the capacitor failed and it exploded. And it made a whale of a mess. So we do not want to see that. But anyway, this is an old capacitor. You find this in old transmitters. This is a mica capacitor, very, very stable. Here's a cheap capacitor. Yeah, I forgot what flavor this one is. Let's see what else we can find here. Here's a transmitting capacitor. This is 3000 volts, 0.005 microfarad. Or that would be, is that 5 nanofarad? Anybody know? I don't know. I'll tell you something. This is one of my favorite here. This is what's called a doorknob capacitor. But if you have a 1500 watt amplifier, this is probably what couples the output of the tube to the Pi network, which then goes out to the antenna. But it's this is a 7.5 kilovolt, a very, very high voltage at 20 picofarad. That's 200 microfarad. I shouldn't use that because you modern people won't ever run into that. Those old timers know. Anyway, disc ceramic. This is a disc ceramic capacitor, but here's various ones. Here's a 0.05 microfarad. And this is what's called a feed-through capacitor. You mount this on an aluminum. Usually your things are built with aluminum. You mount this part on aluminum and you feed a signal through, and this is a capacitor. And so if there's any signal on this side, it gets passed down the ground and it doesn't come out on this side. But very handy for those who like to build things. So now for this little guy. This is a trimming capacitor. Little tiny plates on the back side, little screwdriver slot, and you can twist it and you adjust something. You'll find those inside of your HF and VHF radios. Don't mess with them. If you know what you mean. Now this I have to show you. This is a surface mount capacitor. One of these capacitors could easily be, well, actually, this is 10 nanofarad, which is 0.0001 microfarad, I believe. Don't hold me on that. But it's probably the same as one of these guys here in value. But these are usually installed with machines, and the machine peels this off. And when I have to do it, I have to do that. But there it is. That's what's inside of your handy talkie, your little handheld radio. Most of the parts are that kind of size. The way they're built, they set it up, they got a PC board. They have a machine that strips all these out, gets them all ready, and it just inserts them all over the board. And there is solder on the board. And then they run it through heat. The solder heats up. And even if this is a little bit cockeyed, when the solder melts, it just lines up with where it should be and falls into place. And so all of this stuff is just, it's machine installed. And they just run it through a heat source and it becomes a PC board, and then they assemble the radio. It's as I said, it's all done by machine. If you tried to build something like this by hand, don't shake like I do. It does not work well. Okay, anybody got any questions about all these capacitors? Especially this little guy right here.
In that string, how many capacitors would you say there are in that?
Oh, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, there's 10, 20, 30.
Okay,
But this would be a string that's many feet long. And they bring it up to the machine and they just feed it in. And then the machine just peels them out.
Those would be rated at a very low voltage, right?
Well, no, these are probably 25 volts or so.
Okay.
so you could use them just about anywhere.
Yes, yeah. But there are all kinds of capacitors. And just so you get the little one and the high voltage one. Most of our bypass capacitors and coupling capacitors and stuff like that, it's not critical what they are. However, many capacitors are used in oscillating circuits. Many of them are in critical voltage division circuits. They are in tune circuits. Capacitors are going to change their value with temperature. So there are different kinds of temperature compensation. I only know of these things because in the process of building various things, I've had to figure out the proper kinds of circuits. So anyway, here pretty quick, we're going to have Daron give us a demonstration of series and parallel capacitance. So let me get back to, we have these plates, as you can see. On this one, this is negative Q, or this is the negative side that the electrons flow to. So if you got a battery out here, and the negative side, we'll pretend this is a battery and this is the negative side and it's hooked up over here, it'll move electrons to this point here because this side will be hooked up to the positive side of the battery, which it will attract electrons to this plate here. So this plate will be charged with negative electrons and this plate will be charged with holes. And you end up with an electric field across here. Now remember I said DC, it blocks DC. DC can't flow through this. But AC can. And we'll get into that in more detail next week. Now, here's Now, hopefully, you all will get this. If you hook capacitors in parallel, how do you figure out this secret? It's the same as resistors in series. So if you've got a 50 microfarad, a 20 microfarad, and a 10 microfarad, that's 50 plus 20 plus 10. That's 70, 80 microfarad. It's that simple. But if, see, like this, just C1 plus C2 plus C, however many you put in parallel, you just add them all up. You might have a 220 microfarad electrolytic and then put a 0.001 microfarad capacitor in parallel with it. Won't make any difference except for when it will pass. But that's a whole nother story. But capacitors in series, another secret. It's the same as resistors in parallel. So if you remember how to figure out what the capacitance is in series, you just use the same formulas you use for resistance in parallel. Okay, Daron. Daron, you're on.
All right, Joe, what do you want me to build?
Oh, well, let's see. Well, let's just start, like resistors, we started with them in series. Let's take them, let's put them in parallel.
So you want 3 of these?
Well, let's just stick one in and measure it.
Okay. So we'll be sure that we find the negative side with the little stripe on it there. It's the shorter of the 2 leads if you haven't cut yours yet. And we'll just drop it in the circuit board here. You wanted me to measure the voltage or just measure the capacitor?
Just the capacitor.
All right, well, let's see.
I don't think we need to get into measuring the voltage yet.
Okay,
That's just kind of a esoteric subject anyway.
we will set the meter on capacitance and see what happens. That's pretty close to 100.
Yeah, these capacitors surprised me. Mine were all really close to 100 microfarad. Okay, now plug in the next one.
Well, I'm going to change my meter setup here so that it's a little, I can get those wires out of the way a little bit. All right, so we've just got 1 in there.
There we go. Okay, now let's put 2.
Okay, there's
Series.
2 in series. Or parallel, sorry.
Parallel.
So that, yeah.
Yeah, thanks for
Well,
correcting that.
That's 203.
Pretty close, huh? And 1 more in there.
Yeah. Let's see what happens.
.303, look at there. Pretty close.
300
304.
microfarad. 3 capacitors in parallel. What does that remind you of?
Resistors in series.
Yeah. So if you've got the resistors in series figured out, hopefully, you can apply that to capacitors in parallel. Daron, do you have a couple like 50 microfarad?
I've got the 47 and a 22 or something here.
Yeah, okay, well, the book was using 20 and 50, but the standard values are 47 and 22. So let's stick the what one you got in your hand there?
47.
Yeah, stick that one in there. Measure it.
All right. So there's the 47. We think, we'll see.
Yeah,
49, that's pretty close.
yeah, that's actually, that is quite close for a cheap electrolytic capacity. Now stick the 22 microfarad in parallel with that.
You want to do the calculations first?
Oh, sure, tell us.
Oh, I don't know.
Well,
I'm the practical guy, Joe.
well, yeah, but you're supposed to be learning here too. What do you
Any
do?
math that has letters and stuff in it, I don't do. So
Somebody. Oh, I see a hand back there. Chuck, Bruce?
Not me,
No, not you.
the other guy.
Oh, come on, somebody tell me.
72?
72, yeah. It should be
you gotta
72.
say it with authority though, John.
72.
There we go.
Oh, look at that. Hey, good shot, John. Okay, now let's take those two capacitors and put them in series.
All right. Now let me,
Now, somebody want to guess before he hooks it up, what the value ought to be?
What were they, 47?
36.
It's not 36.
Oh, no, you're right, because I gotta do, yeah, you gotta write this.
Remember resistors?
Mhm.
And when we put them in parallel, what happens when you've got resistors in parallel? What is the
It's always
resistance?
less than the lowest one.
Yes.
Exactly. So what would you expect this one to be?
Lower than 22.
Lower than 22, correct. And Darren, oh, you're doing such a good job of hiding that.
Oh,
Let's see what it is. 15.5. So those are two capacitors in series. It's less than, and in this particular case, since it's two capacitors, you can use that C1 times C2 over C1 plus C2 and come up with the value. If you have three capacitors, you got to use that crazy thing, 1 over C1 plus 1 over C2 plus 1 over C3 plus et cetera, et cetera, et cetera. But if you're, Darren has a method which is actually very effective. If you've got a capacitor and it's too much and you want a little less, just grab a capacitor and stick it in series and see what you come up with. If you get too little, make the capacitor smaller. Wait a minute, bigger. If it's too high, make the capacitor smaller.
yeah, now you're talking my language, Joe.
Yeah. In all practical stuff, you can do that. Or you can calculate it out by hand. But the Darren's method is you have to have a stash like mine.
Yeah, gotta have the
Darren
parts.
laughed. I guess I'll have to photograph my shack and show you guys. Oh, how much time we got here? About 5 minutes? Yeah, we've got 5 minutes
Yeah.
left. Let's, Darren, thank you
Yes,
very
sir.
much. Anybody got any questions for Darren and what he's doing there? We got silence?
I have a question. So I was confused when you said that DC doesn't pass through, it gets blocked by the capacitors.
Yes.
But in our original circuit that we built, didn't we have two small capacitors in there? Wasn't that a DC circuit?
Oh, you're talking the regulator that we had at the beginning?
You're talking about this regulator here, right?
Right.
Well, the two things that are right in front of it, aren't those
Yes.
capacitors?
Yes, so the confusing thing about this is how they are connected. Whether the circuit goes through the capacitor or
Uh-huh.
whether the capacitor is connected to ground.
Ah,
In both of these capacitor situations where the regulator is, the capacitor goes from the positive voltage side to ground.
uh-huh.
So it bypasses.
Darren, pull your sheet up and show this.
Oh, sorry, yeah.
See how they're hooked up?
Yeah, so they're from this is the plus side and this is ground down here.
Okay,
So the current, the blocking part would happen if you're trying to go through it. We're just charging it up like a battery in
I
this
see.
situation. It is confusing because I was telling Joe that my Elmer always referred to these and inductors as the traffic cops of radio. They block AC and pass DC, and the other one passes DC and blocks AC, or whatever the way it works. But it is confusing with the capacitor for me
uh-huh.
because they do different things, whether it's going to ground or whether it's the current is trying to go through it.
I see.
That's really not a good explanation. Sorry.
Actually, I thought it was excellent.
Okay, that's how I view it anyway. It definitely blocks and passes as it's supposed to, but it's how you use it in the circuit that makes the difference.
So how is it, and when you have a 9-volt battery, you're gonna enter both AC and DC? I don't recall how that happens.
That's some magic. Joe's going to crank a little wheel and generate that into AC power somehow.
Okay.
We'll have to do something else to generate the AC.
And I'm sorry, I was thinking about something else. Repeat your question.
I was just asking, we've got a 9-volt battery. How is it that we're introducing both AC and DC into this circuit here?
We will not be introducing AC into this circuit. It's just, this is going to be strictly DC as far as I know. And I will do some demonstrations with AC coming up. So allow me to remove the pin. There we go. And I think this is a good way. We've got just 1 minute left, but any other questions, anybody? Satisfied or totally confused? Well, Anne, thank you. She says it's starting to make sense. I hope so. Hey, look, I sent out an email. I don't know if all of you have read it. Some of you, you're not totally going to get this. And I understand. I mean, especially if you're just starting out.
Thank you for understanding, Joe. I'm just not going to get all of it.
Oh, shut up.
I'm not going to do the math. I'm not good at it. I'm not going to do it.
Oh,
Amen, you're not alone.
well, we all have trouble with the math. I do a little better at it, but
Bruce and I are going to sit over in the corner and keep swapping out parts until we get it to work.
You got that right. Take care of yourself.
but you know,
Right here, man.
if you learn the vocabulary and you learn what people are talking about, you might not be able to actually work with it, but you will understand what they're talking about and have some idea. So you're not totally snowed. When we get done with the class, we're going to have two kinds of people. We're going to have people who's going to take this and they're going to run with it. They're going to apply it to their station and their moon bounce or whatever they do. I mean, and it'll be wonderful. There will be some of you that are just technicians and you've got your handheld. But I want you to know when people are talking about a 6 dB gain Yagi antenna, you will know what they're talking about. And you'll know that'll apply so that you can get into the repeater with your handheld from 30 miles away. You know, so just hang in there, learn as much as you can, and then I hope you enjoy the class. God bless everybody and thank you.
Thank you, Joe. Thank you, Darren.
Thanks, Joe.
Appreciate it, guys. Good night.
Thanks, Joe.
Thanks.